Sometimes in engineering, we may have to deal with complex valued entities, like in electrical engineering, you may have to deal with phasor, or in telecommunication, baseband representation of signals. So this is why we need to be able to work with complex random variables. Indeed, complex random variables are nothing like if you have a random variable, it has a real part, Z1, it has a real part, which is a random variable, and it has another imaginary part, which is another random variable. The same applies to Z2, a second random variable, and so on. So if you have a bunch of complex valued random variable where real part and imaginary part are random variables, so we denote Z, the vector Z, as Z1, Z2, Zn. So this is a vector which is equal to x1, x2, xn, and plus j is the square root of -1, and then you have y1, y2, yn. So in fact, this complex random vector z is equivalent of having two random vectors. So you could say that z is equivalent with concatenation of x and y, so x and y, where this vector x is this one and this y is this y. So in fact, a complex random vector of length n is equivalent of a real random vector of length 2n. So if you have the joint distribution of this vector with length 2n is to have the distribution of the complex random vector. So the joint distribution of these complex random variables is determined by the joint distribution of the random vector x and random vector y, which is like a vector of size 2r. So we say that these random variables zi are independent if this joint distribution can be grouped: joint distribution of x1 and y1, joint distribution of xn and yn, and so on. So if you could decompose this distribution into a function which is only a function of x1 and y1 and x2, y2, etc., then we call them independent. So the mean of a function of this random variable is given by that. So this was when these values are real random variables. So if you have complex random variable, you have to do the same thing. So instead of n random variable, you have two n random variables. N of them are real part and the other n is imaginary part. So if you have zi as complex random variables, then the mean of a function of them is here. The only difference is that you have to run the joint distribution of joint PDF of not only real parts and imaginary parts. So you have two n random variables. So you have two n integrals. So this is why you have dx1, dy1, etc. And then you have to put, so this notation means you put integrals like that, two n of them. So you see that this integral is a linear function of these. So if you have expected value of a linear combination of two functions of these complex random vector, you can easily prove that one. So expected value operator is a linear function.